Today, we move beyond simply building AI models to evaluating their reliability. In biomedical engineering, a model must perform well on new patients and data, not just training sets. By the end of this video, you will be able to select metrics, identify overfitting, improve performance, and explain your model's predictions. Mastering AI requires focusing on 5 pillars: defining what makes a model good, selecting the right metrics, managing bias and variance, optimizing training through tuning, and ensuring explainability. These areas are vital for building trustworthy, real-world biomedical applications. High-quality models must balance 2 critical needs: generalization and scalability. Generalization ensures the model performs well on unseen data, while scalability guarantees it remains efficient and stable when handling large volumes of real-world data in environments like hospitals or clinics. Choosing the right classification metric is essential. Precision helps minimize false positives, while recall is critical for minimizing false negatives in life-saving screenings. The F1 score provides balance for imbalanced data, and the Matthews correlation coefficient offers a comprehensive view across the entire confusion matrix. When dealing with regression, we rely on MAE, RMSE, and R-squared. While MAE is intuitive as it shares the target unit, RMSE heavily penalizes large errors, making it highly sensitive to outliers. Choosing the right metric depends on the clinical importance of those outliers. To visualize discriminative power, we use the confusion matrix to map correct and incorrect predictions. Simultaneously, the AUC-ROC curve evaluates the model's ability to separate classes across various thresholds. Both tools are necessary to ensure a model is both accurate and clinically safe. A significant gap between training and test accuracy is a hallmark of severe overfitting. This occurs when a model memorizes training noise rather than learning the underlying signal. In biomedical AI, this is dangerous, as the model may fail when applied to real patients or new clinical environments. We must locate the complexity sweet spot to balance bias and variance. An overly simple model underfits, while an overly complex one overfits. The goal is to find the level of complexity that minimizes validation error, ensuring the model generalizes well to new, unseen problem sets. To combat overfitting, we use active interventions. L1 and L2 regularization apply mathematical penalties to keep weights in check. Early stopping halts training when validation errors begin to rise, and dropout randomly disables neurons to encourage the learning of robust, redundant patterns within the network. It is important to distinguish between parameters and hyperparameters. Parameters are learned automatically during training, such as weights and biases. Hyperparameters, like learning rate and batch size, are set by the engineer beforehand and dictate how those internal parameters are learned. When searching for the best hyperparameters, we have several options. Grid search is systematic but slow. Random search is often more efficient for large spaces, while Bayesian optimization is the most intelligent approach, using prior results to predict which configuration should be tested next. Model optimization is a continuous life cycle, not a single event. It involves defining the search space, evaluating configurations, and constant monitoring post-deployment. We must watch for data or concept drift, as changes in patient populations or hardware can degrade performance over time. Interpretability refers to models that are inherently understandable, like decision trees. Explainability, however, refers to post hoc techniques used to clarify why complex black box models like deep neural networks reached a specific decision. Both are essential for biomedical AI transparency. Modern XAI frameworks are vital for audits. SHAP helps allocate credit for predictions across input features fairly. LIME approximates local logic for individual cases, while GradCam creates saliency maps to show exactly which parts of an image influenced a model's classification decision. To conclude, accuracy alone is insufficient for deployment. True trust is built by synthesizing metrics, optimization, and explainability. Mastering these pillars transforms an unpredictable black box into a reliable, accountable engineering asset, capable of safely supporting human clinical decision-making.